All right. I want to wrap up this section, this video, with one last example. In this case, a constrained optimization problem. The question again is posed on the slide. I'll summarize it by quickly. We have a farmer is trying to decide how to divide 200 acres that's available for planting between two major crops, wheat and corn. Corn costs more to produce. It requires 4 worker days, that is one worker working for 4 days of labor, and $200 of capital for each acre planted. Right? The capital going into seed and water and fertilizer and so on. Right? Wheat, on the other hand, requires only a single worker day of labor and $100 of capital for each acre planted. So corn costs more to produce than wheat, but corn produces more profit. Corn produces a profit of $600 per acre, while wheat produces a profit of only $400 per acre. Now, you might say, well, if corn produces more profit, plant corn. There are constraints on this farmer's decision, though. The farmer only has available $22,000 of capital. That is how much money they have available to spend. And they have 320 worker days available of labor. Right? They do not have anything more than that. If those are the constraints, this is how much capital they have, this is how much labor they have available, what is the best planting strategy? Start off by trying to write down this problem as an equation, or as a set of equations. These are going to be a little bit different because of the nature of the problem. We're not going to so much get equations as inequalities. Start with the variables. Variables are the unknowns in the problem. How many acres of wheat and corn should be planted? Another unknown is the profit. What is the profit? Define variables for each of these. Let X be the number of acres of wheat planted, Y be the number of acres of corn planted, sorry, and actually I just noted there's a little bit of an inconsistency on this slide with the equations. So I'm going to correct this. This should be, sorry, not very good with writing this. This, X should be acres of corn, Y should be acres of wheat. There we go. I will correct these on the slides that are posted. So X be the number of acres of corn, Y be the number of acres of wheat, and P be the total of profit. After we've done this, we can summarize all of the information here in a series of equations or expressions. One for land, one for labor, one for capital, and one for profit. Land, the number of acres planted of corn and the number of acres planted of wheat has to be less than or equal to 200. That's how many acres of land is available. Right? We can't plant more than 200 acres total. Each acre of corn requires 4 worker days of labor. Each acre of wheat requires 1 worker day of labor. So 4 times x plus y is the total amount of labor needed. This has to be less than 320, the total amount of labor available. Each acre of corn requires $200 of capital. Each acre of wheat requires $100. 200x plus 100y has to be less than or equal to 22,000, the total available capital. The profit would be $600 per acre of corn plus $400 per acre of wheat, 600x plus 400y. Important to note that the first 3 expressions are inequalities that have to be satisfied. These are what we call the constraints. The last expression is the profit. This is what we call a target function. We would like to maximize this, make it as large as possible. So we might summarize the problem. If x is the number of acres of corn and y is the number of acres of wheat, since I have it correct here, and p the total profit, we want to maximize p equals 600x plus 400y, subject to the constraints that x plus y is less than 200, 4x plus y is less than 320, and 200x plus 100y has to be less than 22,000. What do we really want to do? We want to find the values of x and y that make the profit the biggest while still solving this problem. This is a so-called linear programming problem because we have linear equation as the target function and linear equations as all of the constraints. It turns out that actually one way of solving this kind of problem is with graphical analysis, essentially drawing a picture that lets us show what are the allowed answers. How does that really work? Well, each constraint can be thought of as a line in a plot of x versus y. X plus y is less than, this should be sort of, sorry, I'm getting a slight error that I will have to correct. Sorry. Less than or equal to, erase pen. Less than or equal to 200 can be rearranged to y being less than or equal to 200 minus x, 4x plus y being less than or equal to 320 can be rearranged to y being less than or equal to 320 minus 4x, and 200x plus 100y less than 22,000 can be arranged to y is less than 220 minus 2x. We can plot each of these straight lines and note that the allowed solution requires us to be below that line. The y value has to be below the value specified by these. We should also note that there are a couple of implicit constraints here that we haven't written down. That is that x has to be greater or equal to 0 and y has to be greater or equal to 0. We can't plant a negative number of acres of anything. Right? So what happens when we plot these? Here I've shown our 3 equations, 200 minus x, 320 minus 4x, and 220 minus 2x. We're going to identify them based on where their intercept is, 200, 220, 320. and only the shaded region is allowed by the constraints. We have to be underneath all of the lines. So that's kind of this region here. We have to be, and in the positive. Right? So any answer outside of this area, say over here, would violate the constraints. Can't be our answer. We also should note that if we increase X or Y, or both, we have to increase profit. Planting more of something has to increase the profit we have. So if I start here, I can always move up, and that would increase profit. I can always move to the right, that would increase profit. And so the only place where we know we can't necessarily move up or right is when we're on one of these lines. This tells us that the highest profit has to lie somewhere along these boundary lines. It actually also turns out that moving along one of the lines has to either increase profit or decrease profit. Right? And once we've identified the direction, essentially, so if we think about, say, moving along this blue line, we're increasing the amount of corn produced, but we're decreasing the amount of wheat produced. Depending on the slope of this line, we might ask, is the amount of corn that we plant, that we increase, enough to compensate for the amount of wheat that we lose? If that's the case, then moving in this direction along the line will increase profit. If it's the other way around, moving along this line in this direction would decrease profit. Since moving along a line will either increase or decrease profits, the highest profit has to end up at one of these intersection points. That if we're here, I can't, and I don't necessarily initially know whether moving along this line in each direction will increase or decrease, but I know that it has to be one of those two. Unless, of course, there actually is a slight caveat that if the slope is exactly the right way, maybe moving along the line doesn't change the profit in any way. But even there, you will still get a maximum value at the intersection point. This feature allows us to limit our consideration to only the points of intersection. So we kind of draw this picture. We say, okay, look, there are 4 points of intersection. Actually, there's one more for the implicit pieces down here of 0, but planting nothing gives no profit. So that's not likely to be our answer. And so all we really have to do at this point is plug in what these intersection values are, x and y, into the equation. Right? There are, this first intersection point is the intersection of the blue line, 200 minus x, with x equals 0, which occurs at xy is 0, 200. This is the intersection point of the blue line, 200 minus x, and the black line, 220 minus 2x, which gives an intersection point of 20, 180. The intersection of the black and red lines gives us an intersection of 50, 120. And the intersection down here of the red line with the x-axis is 80 and 0. All we need to do is plug these x and y's into our profit equation, and whichever one is highest is our answer. Doing that gives 80,000 for this first point, 84 for this second, 78 for this third, and 48 for this one down here. These are actually all fairly close, but the highest, most profitable point is at this one right here. Profit is maximized when y is 20, 180 with a value of 84,000. This is our mathematical answer we need to put this back into the context of the problem. The most profitable planting strategy is to plant 20 acres of corn and 180 acres of wheat for a profit of $84,000. We note here that even though corn produces much more, we don't have a lot of corn produced. This is because of the constraints. The limiting constraints here are the available land and the available capital. What were the intersection points? It was the land line and the capital line, the blue and the black. Labor is not limiting. We can tell that land is one of the constraints by the fact that we are actually using it up all. We have 200 acres of land. More corn couldn't be planted because it costs too much to do so. Right? There's the labor available for it, but there's not the money to plant enough corn to have more. Right? This not only tells us what the best planting strategy is for this year, but it also, by looking at what the limiting constraints are, would allow the farmer to think about, for next year, what might be the best strategy. Right? He's limited in both land and capital. If he wants to make more, if they want to make more profit, then they would need to obtain more arable land by clearing more land or purchasing more land, and or get more capital. Maybe use some of that excess labor to clear land, or use some of that excess labor to start another business to bring in more capital for planting, or so on. All right.